For my graph, I had a position time graph, and it is a slanting curve that will go up, and it is a quadratic line, quadratic curve. The formula we used was a quadratic equation for the base of the curve, which is y equals ax squared plus bx plus c. And that mathematical formula, which we translated. I then plugged in the ABC into the quadratic formula. The A was 0.56, which represented half of our acceleration, and our acceleration was 1.2 meters squared. The x's in the quadratic equation translated to time, so we multiplied the half of acceleration times time squared, because that is the unit, meter squared. Then we added the bx, so that would be our velocity, so negative 0.09 multiplied by time, because there's an x after it. Then we added the c, which is the y-intercept, so that would be 0.17. From this, the general formula would be 1/2 a t squared plus velocity time plus the initial position, which would be our y-intercept, for a general equation. So the quadratic formula written out would be y equals ax squared plus bx plus c, and our translation with our numbers plugged into that would be half of acceleration, half of a, so 0.56 t squared plus our velocity, negative 0.09 initial velocity, multiplied by our time, because the x's swing down to the time, and plus our y-intercept, which would be 0.17, our starting position, which is right there. Translate. There's our acceleration. There's our velocity, the b. Alright. Our general formula written out would be x equals 1/2 a multiplied by our time squared because that's acceleration, plus our average velocity multiplied by our time again, plus our initial position, which is also our c, dating back to the quadratic formula. And that is our general equation. Circle that multiple times.